Good evening, everyone. This is a quick run-through of homework problem 4.35 for kinematics and dynamics of machines. This particular homework problem describes a 4-bar link, which you can see on the screen. The crank is O1B. It has a length of 1 inch and an angle of 45 degrees with the horizontal. The coupler BC is 3.25 inches in length. The rocker 03C is 2 inches in length, and the fixed length from 01 to 03 is 2.8 inches in length. We are told that the angular velocity of the crank is 35 radians per second, and that is positive, so it is rotating in a counterclockwise direction. As a refresher, remember that we can construct the velocity polygon based on the perpendiculars to these lines. So as for instance, the relative velocity of point B with respect to the fixed frame is perpendicular to the straight line between them. The relative velocity of C with respect to B is perpendicular to the straight line between them. And the relative velocity of C with respect to the fixed frame is perpendicular to the straight line between them. That leads us to create a velocity polygon that looks like this. You'll note that the points on the velocity polygon are labeled with the points that they represent, just in lowercase, so that we can see the difference between the velocity polygon and the base polygon. In this case, we have a line going from our starting point, which for convenience we put at B on the linkage. It is labeled lowercase o on the velocity polygon. This line goes to lowercase b on the velocity polygon, and it is perpendicular to the crank. The next line that we can get is line OC. It also starts at the fixed location, and it is perpendicular to the rocker. Finally, we can draw a line BC. BC represents the velocity of C with respect to B. It is perpendicular to the line BC, which again is the coupler on the figure. It goes from point B, which we know because we have the length for OB, and where it intersects with OC defines a velocity of point C. In this particular case, we find the following from our figure. This is at a scale of 1/10. We were told that the crank is rotating counterclockwise at 30 radians per second. Therefore, the velocity of point B is 35 inches per second. The velocity of C with respect to B, when we measure the figure, is 13.89 inches per second. Making use of the equation V equals omega r, we can solve for omega 2 and see that it is 4.3 radians per second. In the same way, we can measure the distance from O to C, find that it is 23.4 inches per second. Solve for omega 3, and we find that omega 3 is 11.7 radians per second. At this point, we can draw our acceleration polygon. Remember, the acceleration polygon should always be done in the following order, and some of these are already filled out. In this case, we have a 4-bar link, so we will start with the normal acceleration of point B. then the tangential acceleration of point B, the normal acceleration of c with respect to B, the tangential acceleration of c with respect to B, the normal acceleration of c, and the tangential acceleration of c. We know formulas for each of these. All of the normal accelerations are equal to the angular velocity of the link squared multiplied by the length of the link. All of the tangential accelerations are equal to the angular acceleration of the link multiplied by the length of the link. In this case, I've already filled out what we know in this acceleration table. The normal acceleration of point B is equal to 35 radians per second squared multiplied by the length of that particular link, which is 1 inch. So we know that it's 1,225 inches per second squared for the normal acceleration. We always know that the normal acceleration of a point is parallel to the link, and it is going in direction from the moving point towards the stationary point. The tangential acceleration of B in this case is 0 because we are given no angular acceleration for link 1. Similarly, the normal acceleration of c with respect to B can be calculated from omega 2, which we just determined from the velocity polygon. The tangential acceleration, though, we don't know. The normal acceleration of c can be determined. Tangential we don't know. But we do know enough now to draw the acceleration polygon. Let's go ahead and put that in place. Here's my acceleration polygon. Please note that I have a link going from some starting point parallel to the crank in the direction from B on the crank towards the fixed link. That's this highlighted link. I have no other acceleration for point B, so I've labeled that as B prime. This line tells me all of the accelerations at point B. I've also labeled my starting point as O prime. From there, I have the normal acceleration of c with respect to B. That's this little tiny short line here. It is again parallel with link CB on the main figure, and we know its length. Remember, it is very, very short in comparison to all of the others. From there, I know the direction of the tangential acceleration of c with respect to B. It's perpendicular to this little short line, or perpendicular to the coupler, whichever is easier to draw. I didn't know its length when I initially drew it, so I had to go back to the starting point and draw this line, the normal acceleration of point C with respect to the ground. Again, it is parallel to the rocker, and we know its magnitude, considerably shorter than the normal acceleration of B, but longer than the normal acceleration of C with respect to B. From there, I can draw the line that represents the tangential acceleration of c with respect to B. I know that it starts at the end of the normal acceleration vector, and wherever it intersects the tangential acceleration of c with respect to B, that defines my point C prime. Once I have those things, I can measure those points and come up with everything that I don't know. In this case, I can find the tangential acceleration of c with respect to B. My scale factor is very small for this figure. It's 1,000 to 1. So I see then that using this number, alpha 2 is 439.1 radians per second squared. I can also measure my acceleration polygon to get the tangential acceleration of c, and from that calculate that the angular acceleration of link 3, or the rocker, is 713.7 radians per second squared. So that concludes this particular demonstration. Again, this is homework problem 4.35. I urge you all to try this on your own. Take a piece of graph paper, take your ruler. If you have some other drawing instruments, feel free to use them. Take a stab at it. Thanks very much for listening, and I will see you next class.